Hey everybody, this is the second lesson in the counting methods unit. We're going to be learning about something called permutations and factorial notation. So what a permutation is, it's when it's an arrangement of objects where the order matters. So for example, if we have two objects, let's just call them letters instead of objects in this case. If we have the letters A and B, there are two permutations. There's two ways that we can order them. We can either do AB or we can do BA. If we take into account three letters, so say we have ABC, well, this is one arrangement, and we can rearrange these letters to create different combinations. So we could do A, C, and B. We could do BAC and BCA. Or it could start with a C, CAB, and CBA. So when we had two objects, there were two possible permutations. And when we had three objects, so A, B, and C, we had 6 permutations. Now, these numbers are going to be some special numbers. We'll kind of see why in a little bit. But this is just a general idea of what a permutation is. So when we have a certain amount of things and we want to figure out how many ways we can make different arrangements of them. So in example number 1, it says, given the letters A, B, and C, which we kind of did here, we're going to write out all possible 2-letter permutations. So the first one would be AB. We could also have AC. And then if we start with B, we would have BA and BC. And if we start with C, we would have CA and CB. So these are all the 2-letter permutations out of these 3. There are 6 permutations altogether. Okay, 6 different arrangements of these letters. And I want to stress the word arrangement because there's going to be another lesson in the future that also considers this, but the arrangement is not necessary. Example 2, determine the number of arrangements that 6 kids can form while lining up to drink from a water fountain. Now, if we were giving these kids, say, 6 different names, like say we had Alice and Ben and Caleb and Dennis and Edgar and Frank. If you notice, I use names that start with A, B, C, D, E, F. If we tried to make arrangements like this, we would be sitting here all day. So instead, what we are going to do is we are going to, well, it's going to look a little weird, but it's basically based on what we did in the last lesson. So we know that there are 6 kids altogether that are lining up in front of the water fountain. There are 6 possibilities for the first kid. We'll just take any kid. We can plunk them at the front of the line. And once we put a kid here, now we only have 5 options left for the next kid, and 4 for the next one, and 3 for the next one, and 2 for the next one, until we have 1 kid left, and the only spot for him is at the end of the line. So we would multiply all of these together, and we would get 720 arrangements. Now again, the reason why I was saying that, for example, this 2 and this 6 up here are important, or not important, but they're going to be coming up. Same thing with this 720 number. The reason why that is because these are all factorial numbers. So what factorial notation is, it is how we represent the product of consecutive descending natural numbers. So we start with, for example, in this case, 6, and each number that comes after it, we multiply by 1 lower until we get down to 1. So if we were writing 6 factorial, like we kind of did up here, would be 6 times 5 times 4 times 3 times 2 times 1. So instead of doing this calculation, we could have instead done this, 6 with an exclamation point. Now on your calculators, and I can't seem to find my calculator here, so I will grab one. There is a button on your calculator that is a factorial. So on this calculator, I should have really planned this ahead of time. It is right up here. So it's hard to see maybe from where the screen is, but it's an X with an exclamation mark after it. So if I wanted to do 6 factorial, I would do 6 and then shift and get the exclamation mark there, and you get 720. Just going back up to the two examples I did at the top, what we did in the first one with the AB and BA is 2 factorial. The answer is 2. And then when we threw in the third letter, ABC, that was 3 factorial, and the answer was 6. Okay, so this is going to be very important notation. We're going to take a look at 2 examples here and just see how we evaluate factorials. So the first one is very basic. 10 factorial is just we start at 10, 9, 8, 7, keep going down, 3 times 2 times 1. So we are multiplying all of these numbers together. And we're going to do it both ways. So the first way, we are going to write out each of the numbers here. And we get 3,628,800 as our answer. Now, hopefully I didn't mistype anything here. But now if I do 10 factorial, you can see that we get the exact same answer. So make sure that you know how to evaluate a factorial on your calculator. We're going to take a look at example number 4, which says to simplify 12 factorial over 9 factorial, 3 factorial. Okay, so I'm going to start with 12 factorial, which is 12 times 11 times 10, times 9 times 8 times 7 times 3 times 2 times 1. We have 9 factorial, which is 9 times 8 times 7 times 6 times 5, 4, 3, 2, and 1. I'm going to write that in brackets. And then 3 factorial is 3 times 2 times 1. Okay? All right, so the important thing to note in examples like this is when you are trying to simplify, there's a lot of stuff that gets canceled out. So I didn't even have to actually write all of these numbers out. What I could do instead is just say that 12 factorial is 12 times 10, 11 times 10 times 9 times blah, blah, blah. But this part right here is just 9 factorial. Anytime you have a factorial and you start writing it out, you can write it out as a product of whatever numbers and then a smaller factorial. So if I were to rewrite this, 12 factorial is just 12 times 11 times 10 times 9 factorial. And the reason why this is important is because I have a 9 factorial on the top and I have it on the bottom. I just wrote it out. I wrote out all the numbers, but they actually cancel each other out. So what I have left is just 12 times 11 times 10 over 3 times 2 is 6 times 1 is 6. So we get this. And now we can simplify this. I mean, again, you can just use a calculator, but you don't even really need to. Like, you can just use mental math because 12 and 6 cancel each other out. 12 over 6 is just 2 over 1. When you multiply this out, 2 times 11 times 10, well, this is 22 times 10 is 220. Okay, but the important thing to realize in this example is even if you don't have access to a calculator, you can break down bigger factorials into smaller ones and then cancel stuff out with stuff that is in the numerator and stuff that is in the denominator. Now, all of this is leading into what is called permutation notation, which looks like this. We have NPR, so my N number is the total number of objects. My R number is how many I want to arrange. Okay, so for example, when we were doing the water fountain question, we had 6 kids and we were arranging all 6 kids. So that would have been 6P6. We had 6 kids total. We want to arrange all 6 of them. But what if we had 10 kids total and we wanted to arrange 6 of them? we would get something that looks like this. And this is something that we can use a calculator for, or we can use this notation here, which says that NPR, the number of permutations of our objects, is n factorial over n minus r factorial. So if I were to write this in permutation notation, would be 6 factorial over 6 minus 6 factorial, which is 6 factorial over 0 factorial. Now, I'm not going to get into the specifics of 0 factorial, but 0 factorial does not equal 0. It actually equals 1. And there's a very nice proof that kind of goes into why 0 factorial equals 1. I'm going to save that for another day. If you're ever interested, ask your math teacher. It's pretty neat. If we were to write this 10p6 into factorial notation, we would take the 10, that's my factorial, over 10 minus 6 factorial, which is 10 factorial over 4 factorial. And then we can simplify this just like we did the example on the other side. So there might be a question on a quiz or a test that asks you to simplify. This is what it means by simplify. Don't just plug it into a calculator or whatever and find the answer. We really want to see the steps of how you simplify. What does that look like? Okay, so this is going to be a key formula, which I believe they give you on the provincial exam, but I could be mistaken about that. Now, there is a thing here that says how to do it on the TI-83 calculator. We're not using that. We're going to use Desmos, and we can calculate permutations on Desmos using NPR, and then in brackets, we're going to write our N number, and we're going to write our R number. Okay, so for example, I'm just going to switch over here to Desmos. If we want to do NPR of the 10 and the 6, like we did in that we wrote at the top, it equals 151,200 different permutations. And that might seem mind-blowing to you, but again, if you sat down and you had a group of 10 things, of 10 people, and you tried to make arrangements of 6 out of them, you'd be stuck doing it for a very long time. My personal favorite permutation fact is when you have a deck of cards, so there are 52 cards in a deck, there are 52 factorial ways to arrange that deck of cards. And if you do 52 factorial on a calculator, you get a number times 10 to the power of 67. So that is trillions of trillions of trillions of trillions of trillions of possible arrangements of just a very simple deck of cards, which is kind of mind-blowing. And whenever I say that to people, they're like, I don't believe you. Well, try it out for yourself. See if you can come up with all of the arrangements. All right, we're going to take a look at 3 examples here, and then I believe, nope, there are more on the next page. So there are a lot of examples we're going to go through. Example number 1 here. How many 3-letter codes or code words can be made from the letters of the alphabet if no repetitions are allowed? So there are 26 letters in the English alphabet. We want to figure out how many 3-letter codes there are. So how many 3-letter arrangements? So that is going to be 26P3. And again, if you have one of these calculators, there is actually an NPR button on it. You have to press the shift to get it. Or you can use Desmos. I'll show both ways here. So I have 26 and then shift to get the NPR. And then 3 gives me 15,600 possible arrangements. Just going to flip over to Desmos. And so we're going to change our numbers here to 26 and 3. And you can see again, we get 15,600. Now there is another way that we can do this without even thinking about permutations, is if we write our slots out for our 3 letters, and we know that there are 26 options for the first one. There are no repetitions allowed. So I have 25 letters left for the second one and 24 letters left for the third one. So if we do this multiplication, 26 times 25 times 24, we again get 15,600. So that's 3 different tools that we just looked at for this one question that can help us answer a permutation arrangement problem. Example number 2 says, how many different class executives, so we have a president, a vice president, a secretary, and a treasurer. So 4 different positions. How many can be elected from a class of 100 students if Mindy has already been selected or has already been elected as president? So we have 4 different positions. We have our president, our vice president, our secretary, and our treasurer. There are 100 students in total, but Mindy is already the president, so that means there's only one option for the president. But because we've already used that one student, that means there are 99 possible options left for vice president, then 98 for secretary, and then 97 for treasurer. So again, we can just multiply these 3 together. I mean, you can also multiply the 1, but it's not going to change anything. And there are 941,094 different possibilities. Again, another way that we could answer this question is we could say there is one Mindy who's already the president, and then 99 students left for 3 positions. So 99 P3. So if we do 99 P3, you can see that we get the same answer. Sometimes permutation problems are going to involve cases. So this is an example here where it says Angela needs to create a password for her email account. A very good, interesting case study is you should look into password combinations and how long it takes hackers to break a password given different conditions. So that's why whenever you go to make a password for something, they always say you should use an uppercase letter, a lowercase letter, a symbol, a number. The more options there are that they throw in there that they need from you, like those requirements, the harder it is for a hacker to try and break into your account. That's somewhat related to this question. So it says, Angela needs to create a password for her email account. She can use the digits from 0 to 9 and any letters from the alphabet. The password is case sensitive, so she can use both upper and lowercase letters. She has to have at least 5 characters and a maximum of 7 characters, and each character can only be used once. So that means there's no repetition allowed. How many different passwords are possible? So the cases in this case are, she can make a password that is 5 characters. She can make one that's 6 characters. She can make one that is 7 characters. But 7 characters is the maximum. Okay, so for 5 characters, we're going to consider how many options there are. For 6, we're going to do the same thing. And I'm going to leave 7 for now, and we're going to solve that one in a different way. Okay, so for 5 characters, well, each character, she can use the numbers from 0 to 9. So there are 10 digits. There are 26 lowercase letters, 26 uppercase letters. So in total, she is allowed to use 62 characters. And there are no repeating characters allowed. So for the first character, she has 62 choices. Because there's no repetition, she has 61 left, and then 60, and then 59, and then 58. So we'll do this calculation here. 62 times 61 times 60 times 59 times 58 is that really big number there. I guess we'll write it out. 776,520,240. So I went ahead and I wrote the possibilities for the 6-character one as well. But I just wanted to point out that these are all permutations. So instead of doing this multiplication, this one is 62p6. This one is 62p7. So we can just skip right ahead and do these calculations. I don't know if the calculator is going to give us a good answer because these are going to get really, really big. Yeah, so this number is already in the billions. And if we do 62p7, the number is even bigger than that. We're getting into the trillions. So I'm not going to write out all of the answers here. But the point is, how many passwords are possible in these cases? We would add all of the three possibilities together. So 62p5 plus 62p6 plus 62p7. So it's just important to note that things can be broken down into these different cases. Now we have two more examples here on the next page. So sometimes permutation problems are going to have conditions that are attached to them. So here in example number 4, we have a used car lot where there are 7 different models that are going to be parked as close to the street for easy viewing, so as close as possible to show off the cars. So in part A, we're going to consider that there are 3 red cars that must be parked so that there is a red car at each end and another red car is exactly in the middle. So this is a case where we can't really use the permutation formula, so I'm going to write out the different slots. We know there has to be a red car at the beginning, a red car at the end, and a red car at the middle. So there are 3 red cars altogether. There are 3 possibilities for the car on the left side. Then there are 2 possibilities for the one in the middle, and there's 1 possibility for the car at the end. Okay, so that's just considering the red car. We have that red car condition. Then we have 4 cars left over, and it doesn't matter where they go as long as they're not in the red car spots. So I have 4 options in this spot here. Then once I've put a car there, I have 3 left there, I have 2 left there, and I have 1 left there. Okay, so we're going to multiply all of these together. You can also write this out in factorial notation because my red cars are 3 factorial and my remaining cars are 4 factorial. So we can write it like that, 3 factorial times 4 factorial. 3 factorial is 6, 4 factorial is 24. When you do 24 times 6, there are 144 arrangements possible if there is this condition. Now in this one, it says the 3 red cars must be parked side by side. So how many ways can all 7 cars be parked? And this one's going to look a little bit different. But if the 3 cars are parked side by side, they can be in these first 3, in the second 3, in the third 3, the fourth 3, or the fifth 3. Okay? The whole point is they have to always be parked together. So when we do that, we're going to treat them as like one big possible arrangement. Okay? So I have 5 options for whatever the first car is, 4 for the second, 3 for the third, 2 for the fourth. And now these, let's just assume this is my red car group. I would only have 1 possible slot. But it doesn't have to be here. It can move around in this general thing. The point is there are these possible arrangements when we include the fact that the red car they have to be grouped together. But within this red car group, they can still be arranged 3, 2, and 1. So when we actually break this problem down, there are 5 factorial ways to just do general arrangements times 3 factorial ways for the ways that we can arrange the red cars within this group of red cars. So we're going to do 5 factorial times 3 factorial gives you 720 possible arrangements. Let me just double check that. 5 factorial times 3 factorial is indeed 720. We have one final example here talking about a social insurance number, which is a number that you get in Canada, has 9 digits, and we can use the digits from 0 to 9. So if there are no restrictions on the digits, how many ways can we, or how many possible SIN numbers are there if the digits can be repeated? So there are 9 digits in a SIN number, and we can repeat. So we can use any number as many times as we want. So there are 10 digits altogether. This is just 10 times 10 times 10 times 10 over and over again 9 times, which if you go back to grade 9, you can write this as with an exponent, would be 10 to the power of 9, which is 1 billion possible SIN numbers. If digits cannot be repeated, well, that is where our permutation formula is going to come in handy. We have 10 possibilities for the first, then 9, 8, 7, 6, 5, 4, 3, and 2. Or if you prefer, this is 10p9. So let's go ahead and use our permutation formula. 10p9 gives me 3,628,800. Hey, that number looks familiar. I think we did that in a previous example. Okay, so the key things to keep in mind from this lesson is number 1, understand what factorial notation is. Number 2, understand that a permutation is just a specific way of arranging something. So if a question asks you how many arrangements are possible or how many permutations are possible, make sure that you are using the permutation formula.